All right, so welcome everybody. Today's lecture is on divisibility and modular arithmetic. So before we get started, I'd like to introduce to you guys some definitions that you guys should know. So first, we say that a number A is divisible by another number B if the remainder when we divide A by B is 0. So for example, uh, 4 is divisible by 2 because when we divide 4 by 2, the remainder is 0. And alternatively, if we have A objects, we can form groups with B objects each, so no objects are left over. So uh, you should have encountered this idea in when you were studying arithmetic. And for notation, um, we have A with a straight line down the middle, and then B just means that A divides B. In other words, B is divisible by A. So for example, like 2 is like 2 divides 4 and 3 divides 6, so on and so forth. All right, and then next, just like plus and minus, the modulo operator takes two numbers and gives back the result when gives back the remainder when the first, sorry, this is the remainder when the first number is divided by the second, right? So for example, you could have like let's say like 20 mod 7. Well, when you get the remainder of this, 20 divided by 7 is 2 with a remainder of 6. So 20 mod 7 would equal 6 mod 7. Right. Right. And it's also denoted by the percent sign, which A percent B means A mod B or A modulo B, and it represents the remainder when A is divided by B. Right. Now we also have that a prime number is a number with exactly two factors, which is one in itself. And the definition of a factor is a number A is a factor of B if B is divisible by A. And going back to what I was saying before, a prime number is a number with exactly two factors, which means that one of the common misconceptions about prime is that one is a prime. However, one is not a prime because it does not have um, two factors, it only has one factor itself. So it's neither prime nor composite. And this should say a composite number is a number that has more than two factors. So for example, 4 is a composite number because it has three factors, 1, 2, and 4. This should just say it is divisible by at least two numbers. Sorry for this typo. But it should be four numbers. So for example, 4 is composite because it has three factors, 1, 2, and 4. And the prime factorization of a number is a list of primes that multiply to the number. So for example, the prime factorization of 12 would be, well, to derive it, we'd go like 6 times 2 equals 3 times 2 times 2. So that's 2 squared times 3. So that's the prime factorization of a number. Basically, you break it down into its primes, and then these primes should multiply to the number. Right. So let's introduce some theorems or algorithms that you might want to know. So once again, we have the division algorithm, which was mentioned in last lecture, polynomials, but it comes back again for number theory, except this time instead of working with polynomials for the dividend and divisor, we are working with just numbers. And so we say when we divide A by B, we are essentially writing that A is equal to QB plus R, where Q is just the quotient and R is the remainder. And then we have the fundamental theorem of arithmetic, which says that the prime factorization of a number is unique, being that a number can't have two prime factorizations. So for example, 21 would be equal to 3 times 7, right? But there are no other factorization. Oops. My screen just died. Sorry about that. Think the application crashed. Okay. So the prime factorization of a number is unique. So 21 is equal to 3 times 7, but it won't be equal to any other primes that can multiply to it. All right, now let's have some basic divisibility rules. All right, so the number is divisible by 2 if it ends in an even digit. So 0, 2, 4, 6, 8. A number is divisible by 3 if its digits sum to a number divisible by 3. Number is divisible by 4 if the last 2 digits form a number divisible by 4. A number is divisible by 5 if it ends in 0 or 5. Number is divisible by 6 if it's divisible by 2 and 3. A number is divisible by 9 if its digits sum to a number divisible by 9. And a number is divisible by 10 if it ends in a 0. Now, these are the commonly known ones. There's also divisibility rules for 7 and 11. And you can try to come up with those in your own time. But generally, you should know these divisibility rules because they'll help you go through problems very quickly. So you don't have to actually divide by the number to find whether or not it's divisible. You can just apply these rules. Now we introduce a concept called bounding divisors. So for any composite number, it must have at least one prime factor smaller than the square root of the number. So how do we go about thinking about this? Well, for example, well, let's just say at least one prime factor less than or equal to, right? So less than or equal to, right? So for example, consider the number 4, right? Well, 4 would be equal to 2 times 2. And then these prime factors are equal to the square root of the number. But for the numbers, for example, 21, we'll use 21 again. So the greatest prime factor is 7 and, sorry, the least prime factor is 3, and that's clearly less than the square root of 21. So the reason that this is because a number is at least, so let's say n is equal to some, so n is composite, right? So it's equal to some prime times some other prime. And if one of them is greater than the square root of the number, then the other one must necessarily be less than the square root of this number. And the only time that they'll both be equal to the square root of this number is if P1 is equal to P2, right? And there could be more primes too, right? So for example, P3. But if P3 is greater than square root of n, if all of them are greater than the square root of n, then this product will be greater than n. So it doesn't make sense. So at least one of them have to be smaller than the square root of the number. All right. And then here we have a formula for finding the number of divisors of a number if we find their prime factorization. So if we let the prime factorization of a number be p sub 1 times e sub 1 times p sub 2 times e sub 2 to the e sub 2, etc., etc. So the e's represent exponents and the p's represent the primes. Then it has the quantity e sub 1 plus 1 times the quantity e sub 2 plus 1 plus multiplied all the way to e sub j plus 1 factors. And we'll give a very simple example later on to demonstrate this formula. Okay. And then we also have the sum of divisors. So we let the prime factorization of a number be p sub 1 to the e sub 1, p sub 2 to the e sub 2, etc., etc. And then we have the sum of its factors is 1 plus p sub 1 plus p sub 2 all the way to p sub 1 to the e sub 1. And then multiplied by the quantity 1 plus p sub 2 plus all the way to p sub 2 to the e sub 2, etc., etc. And one shortcut that I'll teach you, although you don't have to know how this comes by, but you can derive it yourself just by performing long division, is that this is also equal to p sub 1 to the e sub 1 plus 1 minus 1 over p sub 1 minus 1. And essentially you can derive this by, you can do polynomial division. So what you would do is divide this expression into the denominator into the numerator, and then you would get that, it would have the same expression as the one inside these parentheses. So this is a shortcut, so you don't have to add all the powers, obviously. All right, so let's do some very simple examples to get us warmed up. So first, let's find all the prime factors of 30. Okay, so 30, well, let's see. Let's start with the first few prime factors. So 30 is divisible by 2, right? So that's 15. 15 is divisible by 3, and that's 5. And those are your three primes, right? 2, 3, and 5. Right? And if we were to find the prime factorization, it would just be 2 times 3 times 5, right? 2 to the 1 times 3 to the 1 times 5 to the 1. Right. The second example, we want to find the number of factors of 30. Right? So we have 2 times to the first times 3 to the first times 5 to the first. And if we use our formula, well, 1 plus 1 times 1 plus 1 times 1 plus 1 is 8. Right? So it has 8 factors. And we can just manually check this if you're not certain that this formula works. We have 1, we have 2, we have 3, we have 5, we have 6. Oops, sorry. We have 6, we have 10, we have 15, and we have 30. And that is 30 factors. All right. And now we want to find the sum of the factors of 30. So we can use our formula again. So the prime factorization was 2 times 3 times 5, right? But using the formula, so 2 to the first times 3 to the first times 5 to the first. So using the formula, we have 1 plus 2, 1 plus 3, to the first power technically, and then 1 plus 5, which would be equal to 3 times 4 times 6, which is 72. Okay. And we can check this by summing the factors. So if we go back here, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 5 is 11, 11 plus 6 is 17, 17 plus 10 is 27, 27 plus 15 is 42, and 42 plus 30 is 72. And we can see that this value matches up with the value that we calculated using the formula. So all in all, we should see, oh, this works. Okay, now let's do some harder problems. So let's start off with an AMC 8 problem from last year. So if you guys did the AMC 8 last year, maybe you've already seen this problem. So it says, how many positive integer factors of 2020 have more than 3 factors? So as an example, 12 has 6 factors, namely 1, 2, 3, 4, 6, and 12. Right? All right, so what we can do is first let's find how many positive integer factors of 2020 there are. So 2020 is equal to 2 times 10, 10 equals 2 squared times 505 equals 2 squared times 5 times 1, and 101 is prime. All right. So let's see how many factors there are. Well, there are 2 plus 1, right? So imagine there are 1 exponents for these. All right, and then 1 plus 1, 1 plus 1, which is equal to 12. So in total, there are 12 factors. Now we can approach this problem 2 ways. First, we can list its factors and find those that have less than 3 factors, and then subtract that number from 12, sorry. or otherwise we could just find how many have more than less than 3 factors just by simply looking at the prime factorization. So let's see. What I would do here is so first we know that so first let's count the numbers with 1 factor, right? So the only number that has 1 factor is going to be 1, right? So 1 right, 1 factor, we have 1 number, 1, right? And then how about the ones that have 2 factors? Well, those are going to be the prime numbers, right? So 2 factors, they're going to be the prime numbers in our prime factorization, which are 2, 5, 1, and 1. So there are 3 in here, right? There's 1 up here, right? And now finally, how many have 3 factors? Well, if we look at our formula, we know that the only way that a number has 3 factors is if it's the square of a prime. So in that case, the only number with the only factor of 2020 that has 3 factors is 2 squared, or 4. And this is also 1. Right. So in total, there are 5 factors of 2020 that have less than or equal to 3 factors. Right. And then the problem asks how many positive integer factors of 2020 have more than 3 factors. So what we can do is we can take the total number of factors of 2020 and subtract the ones that have at most 3 factors. So 1 factor, 2 factor, 3 factors. And then we would get the answer to be 7. And this was actually, as I said before, this is actually a problem from the 2020 AMC 8. So if you guys took the AMC 8 last year, you will have seen this problem. And here you can clearly see how helpful like the formula for knowing the number of factors of a number was, instead of actually having to list them out. And you can also see that, you know, we don't have to like, we can see that it's very helpful to not just list it out, but rather use the formula, right? And then use our knowledge of how we know how we can calculate the number of factors of a number to evaluate it rather than listing them out, finding the prime factorization of each factor, right? And you can do that yourself as an exercise to verify that the answer is indeed 7, but we can clearly see how helpful just knowing some basic formulas and knowing some basic concepts can go. Okay, let's do 2 more examples for this section. All right, so we have the number 21 factorial. So if you guys don't know what a factorial is, we know n factorial is equal to n times n minus 1 times all the way to 1, right? And this is defined for positive integers, non-negative integers rather. So one interesting property is 0 factorial equals 1, but that's not necessary to know for this problem specifically. All right, and we'll be talking about factorials more when we go into combinatorics and counting, permutations, stuff like that, right? Those use factorials, but for now we just have to know what a factorial is to solve this problem. All right, so now we know that 21 factorial is what the factorial means. So now let's approach this problem, right? So the number 21 factorial equals some big number, has over 60,000 positive integer divisors. One of them is chosen at random. What is the probability that it is odd? Okay. All right. So let's see. There are 2 possible approaches that we can take with this problem. So one, so obviously none of the approaches are going to be taking that big number and then trying to find the prime factorization of it and then calculating it from there, right? So instead of doing that, what we can do is we can apply a clever trick to find the prime factorization of a factorial, right? So we'll do this problem this way first, right? So there's one more optimal way to solve the problem, but for now, let's use this trick to find the prime factorization of a factorial, right? So the trick is, so 21 factorial is equal to, well, 2 to the something, right, times 3 to the something, times something, right? So, in order to do this, in order to find the exponents, what we can do is we can repeatedly take the floor function. So this exponent here, the power of 2 that divides into 21 is equal to 21 over 2. And then we can take this number plus 21 over 2 over 2, right? And this technique is used often, very often, in fact, in competitive math, or especially the problems that require like fast solving. Less so on Olympiads, but more so on those that require more computation. So for example, this one. You can see that, and this continues until the value reaches 0. And if you don't know what this weird like half bracket thing is, it just means the floor function. We also discussed this in the previous lecture, but the floor function is just the greatest integer that is less than or equal to the number inside the brackets. All right, so now if we apply this technique, we can see that the exponent of 2 would be equal to 10, right? The 4 of 20 over 2, and then the 4 of that over 2, which is 5. The 4 of 5 over 2 is 2. The 4 of 2 over 2 is 1. And the 4 of 1 over 2 is 0. So everything else after that is 0. So this evaluates to 18. So, right, we can do the same thing with 3. So 3, we have 21 over 3. The 4 of that is 7. The 4 of 7 over 3 is 2. Right, and the 4 of 2 over 3 is 0. Right, now let's continue. What is the 4 of 21 over 5? So 21 over 5, the 4 of 21 over 5 is 4. The 4 of 4 over 5 is 0. And then we could continue this process for, this is for 2, this is for 3, this is for 5. And then for 7, you would have 3, right? And the 4 of 3 over 7 is 0, etc., etc. So finally, at the end of everything, we get to the prime factorization of 21 factorial would be 2 to the 18 multiplied by 3 to the, what did I say before? 3 to the 9, right? And then we have multiplied by 5 to the 4th, multiplied by 7 to the 3rd power, multiplied by 11, multiplied by 13, multiplied by 17, multiplied by 19. All right, and essentially this above technique, this repeated flooring technique, can be thought of as using an exponent, right? Because if we simply divide it by the number, well, for example, if you have like 4 factorial, that's 24, right? But if you simply divide, you would get the maximum power of 2 that divides into it would be 2, right? Because 4 divided by 2 is 2. But that's not the case, right? Because the greatest power of 2 that divides into 24 is not 4, but it's 8. Or 2, it's not 2 squared, but rather 2 cubed, right? So 8. And the reason for that is because 4 is equal to 2 squared, which means it contains more than one copy. You can think of 2. So that means you have to take into account perfect powers as well, or multiples of perfect powers. And that's why this repeated flooring technique works. All right. So we have found the prime factorization of 21 factorial here. So let's circle that, right? And now rather than finding the number of factors of 21 factorial directly, right? Because it said it was over 60,000. So obviously you do not want to bash that out. But first let's look at our expression, right? So in the denominator, so it's asking for the probability that it is odd when one of them are chosen at random. So the denominator would be the number of factors of 21 factorial, right? So that would be 18 plus 1, 9 plus 1, 4 plus 1, 4 plus 1, etc., 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 and then 1 plus 1, right? And on the top, we want to find the number of odd factors of 20 factorial. Now, what does that mean, right? So if it's odd, then it can't have a multiple of 2 or a power of 2 in it, right? So that means that we just have to cross this out, right? And the rest, and then the factors of this number here, without the 2 to the 18, is equal to the number of odd factors of 21 factorial, because every prime factor other than 2 is odd, right? So so this is common knowledge, right? If you don't know it, you should know this, like you should know this. So every prime except for 2 is odd, and this and 2, because it is such a special prime, also comes up very often in competitive math. So if you didn't know that, please remember that very well if you want to do well at competitive math. And then we want to find the number of factors of this number, right? And this factors of this number would be 9 plus 1, 4 plus 1, etc., right? But then you'll notice something, right? The factors on top seem to cancel everything after this, right? So if we listed out more, 3 plus 1 here, there would also be a 3 plus 1 here, right? And then etc., etc., etc. So what we can do is we can simplify the fraction, right? So this cancels this cancels this cancels this, etc., etc., and then everything else is canceled. So this is over 1 over 18 plus 1, which is equal to 1 over 19. All right, and that's the answer to this problem. But we have a more optimal way of solving this problem, right? So what we can do instead, let's go back to the top, right? So it says, one of them is chosen at random. What is the probability that it is odd? Now, the first thing that we do is we know that if it does not contain a power of 2, then it's odd, right? And then we also know that the factors of 21 factorial can take on the form 2 to the 0 times some set of numbers, right? 2 to the 1 times some set of numbers, to the 2 squared times some set of numbers, right? Because that's essentially how the formula for the number of factors of a number is derived, right? And that's why you add 1, right? Because you can also choose 0. You can choose 0 through the exponent for the power of the prime, right? And that's why you see the plus 1s inside the parentheses, right? So instead, we know that all of these sets are of equal size to the set that's multiplied by 2 to the 0. And we also know that in order for it to be odd, it has to be multiplied by 2 to the 0. So what we can do instead of having to find the prime factorization, we can just find a maximum power of 2 that divides 21 factorial. And that's easy, right? We just use the repeated foring technique that we used before. So we see that the maximum power of 2 that divides 21 factorial is 2 to the 18, right? Then we know that then there are 19 equal sets of factors, right? So one set is multiplied by 2 to the 0, one set is multiplied by 2 to the first, one set is multiplied by 2 squared, all the way up to 2 to the 18th, right? And then we just have to find the probability of choosing a number from the 2 to the 0 set, not all of the other sets, right? And then what that would be is just 1, right? Because you can choose 1 over the total number of sets, right? So the total number of sets is 18 plus 1 because it includes 0, right? So 0, 1, 2, 3, all the way up to 18. You can count that yourself, but it's just there's 19 sets in total, and you have to choose the one that is multiplied by 2 to the 0. So that is just 1 over 19. And what you can see is instead of having to find the prime factorization and then do all this canceling, what you can do instead is you can just find the maximum power of 2 and then add 1 and put that in the denominator, and we'll take the reciprocal of that. On the other hand, you would have to recognize the intricacies of what it means, like what it really means to be a factor of the number, and then how the factor formula is really derived. So if you're not sure, you can always default back on, finding the prime factorization of the number first, and then finding the prime factorization of the second number, and then dividing the number of factors of one over the number of factors of another. That's fine because you can see that it canceled, everything else canceled, and it ended up working out fine. But as you can see, the shortcut that we take with just identifying that it has to be multiplied by 2 to the 0 is significantly faster, right? Because we don't have to do all these additional steps. All right. Let's do one last example. So it says that 2-digit integers from 19 to 92 are written consecutively to form an integer n equals 1920 21 22 23 24, etc., etc. Right. And then we said, suppose that 3 to the k is the highest power of 3, that is a factor of n. What is k? Well, if we look back at our divisibility rules, we know that a number is divisible by 3 if its digits sum to a number divisible by 3. Number is divisible by 9 if its digits sum to a number divisible by 9. So first, let us determine the divisibility of this number by 3 or 9, right? Because if it's not divisible by 9 or 3, then we can immediately put an upper bound on k, right? So let's right. So let's see. So looking at the ones place, right? Let's look at the ones place first. So it's 9, 9, and then 0, 1, 2, all the way to 9, right? And then this is repeated for the 20s through 80s, right? And then we have 0, 1, 2. Now first, the sum of the numbers from 0 to 9 is equal to 45. And I know this off the top of my head, but if you don't know, you can use this simple formula, right? The formula for the sum of numbers from 1 to n is equal to n times n plus 1 over 2. And you can derive this pretty easily and prove this pretty easily as well using induction. But we'll go over induction in the last lecture of our series. So I'll just show you a visual representation of why this might work, right? So if we draw like some dots, it's a 1, 2, 3, 4, right? And then we continue this all the way to n dots, right? Now consider that we flip this triangle and then we complete like a rectangle with it, right? So then it would have height n, right? Because the first row of the triangle had 1 dot, and the last row had n dots. The square has n rows, right? And how many? It has n plus 1 columns, right? Because when we tile it back into itself to form a rectangle, this with the bottom row with n dots is transported to the top. Then we also have that 1 dot from the beginning, right? So there's n plus 1 dots that form the columns. So in total, this rectangle has n times n plus 1 dots. Now the original triangle was just half of it, so it was n times n plus 1 over 2. And that's just a visual representation of how this works. All right. So the sum of the numbers from 0 to 9 is divisible by 9, right? So because it's 45, right? So 9 times 10 over 2 is 45. 45 is divisible by 9. So if this is divisible by 9, then any multiple of it is also divisible by 9, right? So we can effectively ignore this, right? Because right now we just want to know, is it divisible by 3? Is it divisible by 9? But let's test, is it divisible by 9 first, and then if it's divisible by 3. So because if it's divisible by 9, it's automatically divisible by 3, right? Right. So the sum of this is clearly divisible by 9, right? And then let's look at the other things, right? So 9, and then the other units digits are 9, 0, 1, and 2, right? So 9 comes from 19, and then 0 comes from 90, 1 comes from 91, and 2 comes from 92. So in total, the units digits the sum multiple of 9, we'll call it 9n plus 12. And 12 is 3 mod 9, right? So if we go back to the definition of mod that is in the handout, it's the remainder, right? So 12 mod 9 is 3. We could also write that as 9 times n plus 1 plus 3, right? So we know that the sum of the unit digits has a remainder of 3 when it's divided by 9. And now let's consider the tens digits, right? So there's 20 through 29 has 10 copies of 2 in the tens digit. 30 through 39 has 10 copies of 3, right? So in total, it's 20 plus 30. So these are the sum of the units digit, right? Because it's 2 to 10 times 2, 10 times 3, etc., all the way up to 80, right? And we can use that formula again, right? So the sum of that would be 10 times 2 plus all the way to 8, right? And that is equal to, well, 8 times 9 over 2 is 36, but because there's no 1 in this, is just 10 times 35. So this is equal to 350, right? right? And then we also have 3, 90, 91, and 92, which have 9 in the tens position 3 times. And because 9 is divisible by itself, then we don't have to worry about that actually. And then finally we have 19, which has 1 in the units position. So in total, the tens digits sum up to 351, right? 350 plus the 1 in the tens place from 19. Now we have 351 in the tens places and something mod 3 when something that has a remainder of 3 when it's divided by 9 in the units digit, right? So 351, well, this number is divisible by 9, right? Because 3 plus 5 plus 1 is 9. We can use the divisibility rules again, or you can just recognize that 351 is 360 minus 9, 360 divisible by 9. But alternatively, we can just use divisibility rules once again, right? So 3 plus 5 plus 1 is 9, divisible by 9. Right, so that means the sum of all the digits of this big integer capital N. So if we go back to it for the big number capital N, right? So that's all of them concatenated together. If we go back to that big number, you can see that the sum of the digits is divisible by 3. However, it's not divisible by 9, right? Because this is divisible by 9. 351 is divisible by 9. The sum of the tens digits, it's divisible by 9. But the sum of the units digits are not divisible by 9. That just means that the sum of all the digits is not divisible by 9. Right. So that means 9 does not divide this big N, but 3 divides big N, right? So that means 3 is the highest power of 3 is a factor of N. So that means, go back to the original problem, we have, suppose that 3 to the k is the highest power of 3 that is a factor of N. What is k? Well, we know that 9 does not work, so that's 3 squared doesn't work, right? But we know that 3 is a factor of N, which means that k is equal to 1, right? Because 3 to the 1 is 3. So that means that 3 is the highest power of 3 that is a factor of N, so k is equal to 1. Right? So our final answer is k equals 1. And we can see that this problem was simplified greatly just by simply using divisibility rules. And this was not like an easy problem either, because this is from ASME, AHSME, which is the old version of what is now AMC 10 and 12. Oh, actually, it's the old version of AMC 12, I think, because the other one is called AHSME, I think. But yeah, so AHSME is the old version of the AMCs, or the higher level AMCs. So, and it's like a mid-level problem. So this is not an easy problem, but we can see that it was greatly simplified simply by using divisibility rules. Okay, and now we'll introduce a new concept to you guys. And this is called modular arithmetic. So let's first consider an example using a clock, right? So we know that clock, if you use like AM and PM, they essentially form in cycles of 12, right? And if you use military time, which is basically cycles of 24, but for this lecture, we'll just consider, we'll simply be considering just AM and PM and not military time, right? So if on a normal clock, these clocks wrap around 1 to 12, right? Like on an analog clock, you know, those physical clocks that have rotating mechanisms, those are usually numbered from 1 to 12, right? So for example, if it's 10 a.m. when we started the lecture, and let's say that the lecture goes for 4 hours, which obviously doesn't go for 1 hour, but let's say it goes for 4 hours, right? Well, 10 plus 4 is 14, but 14 is not, you know, a number on the clock face. But everyone knows that 4 hours from 10 a.m. is 2 p.m., right? And the reason that it is because our clocks work modulo 12, right? So 10 plus 4 is 14, and that's equivalent to 2 in modulo 12. Now, what that basically means is the remainder when 14 is divided by 12 is the same as the remainder when 2 is divided by 12. And we denote this using 3 bars instead of 2 bars for a normal equal sign, right? You can see that here, right? We use 3 bars, right? So that means 10 plus 4 is 12, is 2 mod 12. That's basically what it means. But for here, we call it the clock world, right? And the same thing happens for day of the week, right? So if we call Sunday 0, Monday 1, and Saturday all the way up to Saturday is 6, then let's say today is Thursday. Well, what day will it be in 13 days? Well, Thursday is 4, right? And then if we add 13, it would be 17, right? But remember that days of the week work mod 7. Obviously, there isn't a 17th day of the week. Or actually it would be equivalent to 18th day of the week since we indexed at 0. But obviously there isn't a 17th day of the week, right? But what we can do is we can take in mod 7, right? So this would be equal to 6 mod 7. Alternatively, it's also equal to -1 mod 7, which basically means that when you divide a number with negative, that's equivalent to -1 mod 7, it's 1 less than a perfect multiple of 7. And basically what all of these numbers have in common is that they'll be spaced. So 13 and 6 have a difference that's divisible by 7, 6 and -1 have a difference that's divisible by 7. So all these numbers that are, so for example, if we have like, if we have like a mod, if we have a mod b, and then this will be equivalent to, sorry, that's not the correct notation actually. It should be saying a is equivalent to, we use 3 bars because it's modulo, remember, and is equal to a plus kb, right? Or where k is any integer, right? So it could be 0, it could be 1, it could be 2, it could be negative, whatever, mod b. So you can see that here, right? So 13, well, 13 plus -1 times 7 is 6, 6 plus -1 times 7 is -1. So these are all equivalent in modulo 7, right? So 13 is in the future, same as 6 days in the future. And since 7 days is a cycle, 6 days in the future is the same as yesterday, right? And since 6 and -1 are the same. So what is the day before? Well, if today is Thursday, well, today's Saturday, but if suppose today is Thursday, right? Then yesterday would be Wednesday, right? So that means that the day 13 days from a Thursday would be a Wednesday. And that's because days of the week work mod 7, and in the previous example, they worked mod 12, right? And this concept can be used for any arbitrary integers, right? And this entire practice is called modular arithmetic. This type of arithmetic where we only care about the remainders, right? So the key here is to understand that remainders are key when we do modular arithmetic. We don't care about the quotient, we just care about the remainder, right? And similarly, we can do the same thing, right? So if we use the previous example, we had Thursdays 4, right? And then we also have 13 days from Thursday, so that would be 17. And then 17 is equivalent to 3 mod 7, right? And that would be Wednesday if we use the indexing that we used before. So 0 is Sunday, 1 is Monday, etc., etc. Right? Oops. All right. All right, and then modular arithmetic equations are just like normal equations, right? So 3 times 4 mod 7 is 12 mod 7, which is, and then equivalent to 5 mod 7, etc., etc. And then similarly, any number that is not an exponent can also be reduced. So for example, we can eventually reduce it to some number that's less than the base modulus that we're working in. And this is called reduction, right? So we reduce 17 above, right? 17 to a non-negative number less than 7, which is 3, right? And the only thing that we cannot do with modular arithmetic equations is that we cannot divide easily. But we can see that there's also a method for dividing, and that's called using the modular inverse. But for this lecture, we won't be touching on that very significantly. We just want to know that we can add them, we can divide them. I mean, we can add them, we can subtract them, we can exponentiate them, we can subtract them. But the only thing we can't do very easily is divide. The dividing is a whole different topic when it comes to modular equations and modular arithmetic. So let's do a few simple examples to see this in practice, right? So once again, let's use time, right? So a watch has an hours, minutes, and seconds hands. They're just a typical watch. The second hand currently points at 31. If 10 seconds pass, what will the second hand point at? 200 seconds, 21 seconds. Well, basically, we can just use modular arithmetic, right? So what mod is seconds in? Well, the number of seconds in a minute is 60. And then if it's 60 seconds, then 1 minute passes and the count goes back to 0, right? So essentially, that means when it comes to a watch, and when it comes to watch, and when it comes to the second hand is in mod 60, right? And now we just want to know what is 31 plus 10 mod 60. Well, 31 plus 10 mod 60 is 41. Oh, sorry. Sorry for my handwriting. I'm not on a stable surface. Let's try this again. 31 plus 10 is equivalent to 41 mod 60, right? And then 200 seconds after is 231 plus 200, which is equal to 231, which is equivalent to 51 mod 60, right? Because the remainder when 231 is divided by 60 is 51. And finally, we have 31 plus 2021, which is equal to 2052, which is equivalent to 12 mod 60, I'm pretty sure. Because 2020 should be divisible by 6, 2040 should be divisible by 60. Let me just check this in my head real quick. Yeah, okay. Yeah, so it's 12 mod 60, right? And that just, so these are the values that it'll be pointing at. 41 is after 10 seconds pass, 51 is after 200 seconds pass, and 12 is after 21 seconds pass. And you'll notice the modulo is just very convenient for these type of calculations. All right, and it's a way to quantify or put in strictly, mathematical, I guess, terms. Okay, so let's try another one. Represent the following situation with modular arithmetic, and then they'll show the steps of reduction. Find the last two digits of 17 squared. Well, when we find the last two digits of something, we're essentially saying we want to find mod 10 squared of everything, right? Because when we look at the number system, it's in base 10, right? So that means that the units digits is in mod 10, and the hundreds digit is mod 10 squared. I mean, sorry, the tens and the units digits together are mod 10 squared, and then the hundreds, tens, and units digit are mod 10 cubed, etc., etc., because they repeat every. So for example, the last two digits of a number, when you count up, they'll repeat every 100 numbers, right? So that means it's in mod 100, right? So essentially what this problem is then saying is that we want 17 squared mod 100. And we want to reduce this, which means we want to have the expression be a non-negative integer less than 100, right? So 17 squared is equal to 289, which is equivalent to 89 mod 100. And that's just by taking the remainder when 289 is divided by 100. All right, and then let's do one more easy example, and then we'll have one last hard example to close out the class. Okay, so it says simplify the following expression mod 13, 2021 cubed. Okay, so the first thing that we should do is obviously we don't want to expand 2021 cubed. But so first, instead, what we do is we find the equivalent of 2021 mod 13. Well, that would be, if you do 2021 divided by 13, right? We got that the remainder is, let's see, the remainder is 6, I think. Okay, remainder is 6, right? And then that means that instead of using 2021 in this expression, this is equivalent to 6 cubed in mod 13, right? Because we only care about the remainder. Right, and 6 cubed, that's a lot easier to calculate than 2021 cubed. Right, so 6 cubed is, if you don't know this off the top of your head, that's fine. But 6 cubed is 216, and 216 is equivalent to 8 mod 3. Mod 13, sorry. Mod 13. Right, and you can just check this by doing division. And then finding the remainder. All right, so you can see that instead of using 2021 cubed, we can use equivalent mod 13. So 2021 is equivalent to 6 mod 13, and then we can to the power to and then cube that, and then we can use that instead of 2021. right? And you can see that this greatly simplified our calculation. So in the future, if you encounter a problem that's like, what is some big number mod some small number? Well, first you might want to convert it into a more manageable number using modular arithmetic, right? So for example, 2021, you don't want to raise to cube that, but 6, you can cube that, right? In a reasonable amount of time, right? Okay, so you can clearly see the benefits of modular arithmetic, especially when it comes to like big numbers, you can simplify them easily. All right, now let's do one last hard example and then we'll end class. So we have the number obtained from the last 2 digits of 90 factorial is equal to n. What is n? All right. I'm just going to say that this problem is actually very difficult. So if we don't, we might go like a few minutes over time if you're okay with that. It's just like 11:05 maybe. So first, we'll use a very the first thing that you have to notice is that if we take for any integer n, if we have 5n plus 1 times 5n plus 2 times 5n plus 3 times 5n plus 4, we have that this is equal to 25n squared plus if we group the factors like this, right? So if we group 5n plus 1 and 5n plus 4 and 5n plus 2 and 5n plus 3, we get that this is equal to 25n squared plus 25n plus 4 times 25n squared plus 25 n plus 6. Right, so this is equal to sorry, this is equal to right, no, sorry, I was right. Never mind. This is equivalent to 24 mod 25, right? Because 25n squared is always going to be divisible by 25. 25n is always going to be divisible by 25, right? And then we know that n is an integer, right? So essentially, what we have here is that 5n plus 1 times 5n plus 2 plus 5n times 5n plus 3 times 5n plus 4 is always going to be equivalent to negative 1 mod 25, right? Because 24 is equal to negative 1 mod 25 as well, right? And where n is an integer, right? And then we also want to find the number of factors of 10 and 90 factorial that is equal to 90, that is equal, and then because it says we got the number obtained from the last 2 non-zero digits of 90 factorial. So first we have to get rid of all those factors of 10, right? So if we do that, then we find that the number of factors of 10 and 90 factorial is equal to, the factors of 10 are 2 and 5, right? But the limiting factor in this case would be 5, because there are going to be more factors of 2 and 90 factorial than factors of 5 and 90 factorial, right? So we can apply this repeated foring technique, right? And this would just be 18 plus 3, which is equal to 21, right? So equivalently then, we want to find the last 2 digits of 90 factorial over 10 to the 21. And we'll call this number big N for simplicity's sake, right? And then we want N mod 100. Right, so what we can do is we can find n mod 4, and then we can find n mod 100. I mean, n mod 25, and combine them to find n mod 100. And we can do that by using the Chinese remainder theorem, which I'll basically introduce, which just basically says that if you have a number that is like a mod b and then c mod d, etc., and then all of those numbers are relatively prime to one another, or all the base modulos are relatively prime to one another, there is a unique solution that is mod the modulos multiplied together, right? Well, first we know that there are still factors of 2 left in 90 factorial when we divided by 10 to the 21st, because we used 5 as a limiting factor, not 2. So that means when it's mod 2, it'll be 0 mod 2 squared, right? So it'll be 0 mod 4. That we know for sure, right? And then what we want to do is we want to find out mod 25, right? So what is it, mod 25? Well, what we can do is we can divide n by 5 to the 21, right? We can take out we've taken out all the factors of yeah. All right, so if we divide 90 factorial by 5 to the 21 instead, right? And we call 90 divided by 5 to 21. So we take out all the factors of 5, right? And let's call this number m, right? So this would be equal to 1 times 2 times 3 times 4 times 6 times 7 times 8 times 9 all the way to 86 times 87 times 89, right? But then we know that, right? And then because we divide by 5, right? We didn't just take out everything that contains a 5, we divided by 5, right? So that means 5 divided by 1 is 1, right? And then 5 divided by 10 divided by 5 is 2, etc. So we still have those factors, right? So that means we still multiplied by 1 times 2 times 3 times 4. So these are the no 5s, right? These are the no 5s. This is 1 5, right? So 1 times 2 times 3 times 4. This is 6 times 7 times 8 times 9, etc. all the way to 16 times 17 times 18, right? Because that's 90 divided by 5. And then finally, we have it contains 2 5s, right? And there's none that contain 3 5s because the number that contains 3 5s is 125. That's the minimum number that contains 3 5s, and 125 is greater than 90. So we won't be in 90 factorial, right? So 2 5s would just be multiples of 25. So that would be 25, 50, and 75, right? So that would just be 1 times 2 times 3 because we took all the factors of 5 out, right? And then what we can finally do is we can use our observation from before, right? Well, 1 times 2 times 3 times 4 is -1 mod 25, right? So all of these are, then this is equivalent to, right? This here is equivalent to -1, right? To the 18th power, mod 25, and that's just 1, right? So this is 1, right? Mod 25, right? Right? And then this, what is the 1 with 1 5 equal to? Well, this is equal to -1 to the 3rd power times 16 times 17 times 18 mod 25. And this is just equal to 6 mod 25. Right. Now what we can do is we can combine everything together, right? We can take the product of everything, right? So we have 1 times -1 times 16 times 17 times 18 times 6 mod 25. And now this is much more manageable compared to before, right? So 16 times, so this middle expression here turns out to be equivalent to -21 mod 25. And I'll skip the calculation, but you can check this yourself just by multiplying and finding the remainder. And then the other one, 1 times 2 times 3, evaluates to 6, right? So we have 1 times -21 times 6 mod 25. And then finally, what we can do is we can reduce this one more time, right? So this is -126 mod 25, which is equal to 24 mod 25. So we know that m is equivalent to 24 mod 25, right? And m is also equal to n times 2 to the, what was it, 2 to the 21, right? So now what we want to find is what is 2 to the 21 mod 25, right? So we know that 2 to the 10, if you don't know this off the top of your head, it's okay. But most people who do competitive math know some perfect powers really well. So 2 to the 10 is 1024, right? And 1024 is -1 mod 25. And that means to the 20 is -1 squared mod 25, right? So that's 1 mod 25, and then 2 to the 21 would be just 2 mod 25. So that's equal to 2n mod 25. Right, and remember that before that we said we can't divide, right? What we can do is we can use, but it actually turns out to be okay this time because we know that n is to be some value from 0 to 24 mod 25. And if we check these values of n repeatedly into we check those values repeatedly, we find that n has to be 12 mod 25, right? Because 2 times 12 is 24 mod 25. And alternatively, 2n, and assuming n is in reduced form, right? So that means it's a value between 0 and 24. Then 2n can take on a value anywhere between 0 and 48, right? And then 24 mod 25 can be 24, or it could mean that 2n is 49. But 2n, n is an integer, it can't be 49, right? Because 49 is still not divisible by 2. So clearly n has to be, n is equivalent to 12 mod 25. And now we finally combine everything, right? So we want to find, so what did we want to find originally, right? What we wanted to find originally was n mod 100. And what do we know? Well, n is equivalent to 0 mod 4 and 12 mod 25. And what we can do is we can use the Chinese remainder theorem, which basically means that there's a unique solution that is mod 4 times 25, and that is between 0 and 4 times 25 minus 1, right? So that would be equal to, that's equivalent to 12 mod 100, right? Because it can either be 12 mod 100, 37 mod 100, 62 mod 100, or 87 mod 100, right? Because there's 12 mod 25, right? But the only one there that's divisible by 4 was 12. So the final answer is, n is 12 mod 100. And if we finally go back to the original problem, what this essentially means is that the number obtained from the last two non-zero digits, right? The number obtained from the last two non-zero digits of 90 factorial is equal to 12. And that's it for this problem. I know this problem was hard and a bit long, but I hope you guys learned a lot from because we used basically everything we learned in this lecture, right? We used modular arithmetic, we used we used polynomials again, right? And we used the factorial, like the repeated foring technique for the factorial. We used a lot of clever algebraic manipulation, and I even introduced you to the Chinese remainder theorem, right? But so yeah, that's basically it for this lecture. If you want to stay back or you have any questions, please do so. Otherwise, you're free to go.